Hello, today we're going to be doing some questions on potential dividers and direct current circuits. So there are a few equations that are really important to remember. So this is how you find your current in a direct in a potential divider current circuit. In the case of this diagram here, this would be our voltage in. Our voltage out would be between these 2 points. This would be our resistor 1 and resistor 2 is the other resistor in the circuit. Then we have V equals IR, which takes into account this sort of segment of circuit where the voltage out, the potential difference between point P and Q, is going to be given by the total current of the circuit multiplied by the resistance of this resistor. Then to find the potential difference out, you can also use you've got your voltage in coming here, your voltage out's there, your resistor 1's here, your resistor 2 is there, and yep, that's essentially how it goes. So I'm just going to jump right in and start answering some of these questions. So we've got to find the potential difference between terminals P and Q. So that's going to be V out, and that is equal to R1, which is 15 kilo ohms. So we've got 15 times 10 to the 3, times by the voltage coming in, which is times 12 volts. And I'm going to get rid of volts there, sorry. And that's going to be over the sum of our two resistors. So that's going to be over 20 kilo ohms. So 15 times 10 to the 3 over 20 times 10 to the 3 is 3 over 4. Multiplied by 12 is going to give us a final answer of 9 volts for the first question. Now, I'm just going to make all of these a bit smaller once I've done them, just to give us room to work. I would highly recommend having a go at these. Well, that didn't really work. I'm just going to have to move them. I don't know what's going on. Anyway, doesn't really matter. So, oh yes, I would recommend having a go at these yourself, pausing the video, and then I'll go through them afterwards. This is the question that we made an error on. It was definitely quite a small error. If we go through the question, highlight what we actually need. So we've got a circuit, and it's providing a voltage which depends on the brightness of the lighting in the room. So we've got a battery with an EMF of 12 volts, negligible internal resistance, and the light sensor is a light dependent LDR. The resistance of the LDR is 5 kilo ohms in the dark and 20 kilo ohms when illumination is maximum. So the variable resistor, which is this one here, is initially set to maximum resistance of 5 kilo ohms, and show the value of the voltage V, which is our V out, when the illumination of the room is a maximum is about 0.4 volts. So this is not easy. It's a relatively tricky question. So the first one we need to do is figure out what the resistance is of our parallel circuit. So these two here. So we've got our LDR is 0.2 kilo ohms, and that's going to be 1 over 0.2 plus 1 over 5. I'll do times 10 to the 3 for kilo ohms is equal to 1 over our parallel. So that's going to be, I'm just going to put it into my calculator here. Bear with me. 1 over 0.2 times 10 to the 3 plus 1 over 5 times 10 to the 3 is equal to 13 over 2,500. So then 13 over 2,500. So RP is going to be 2,500 divided by 13, which is equal to, divided by 13, 192 ohms. Okay, so now we found out what our R1 is in terms of these equations here. So we need to find out what our V out is. So we've got V out is going to be equal to R1, which is 192, times our V in, which is 12 volts, over R1 plus R2, which is 192, plus 5 kilo ohms, which is 5,000. Putting all that in, we're going to have 192 times 12 over 192 plus 5,000. And the total answer is equal to 0.444 volts, which is not equal to, but roughly equal to 0.4 volts, and that is our answer. So then we're asked, the variable resistor acts as a sensitivity control for the circuit. By changing this resistance, the voltages obtained for illuminated and dark conditions can be altered. Explain why reducing R to its minimum value of zero resistance would not be a good idea. So the level of detail you go into here would completely depend on how many marks are given for the equation, for the question. So the best answer you can give is using numerical figures. So whenever the resistance is zero, we can say that the voltage across our LDR, the resistance of this is zero, so then the voltage is going to be equal to 12 volts coming through that LDR. If the voltage is 12 volts, then we can look at we can then find the current, and if we have the current, we can use P is equal to IV to find the power. Essentially what you'll find is if it was reduced to zero, the power would be very high and could be dangerous, or break the component of the circuit. That's the sort of answer that you need to give. I'm not going to go into the numerics just because I don't want this video to go too long, but that would be what you'd be looking to do. Okay, question 3. It is required to provide a voltage supply, continuously variable from 0 to 6 volts, a fixed 9 volt supply, a rheostat, which may be used as a potential divider. So a rheostat's essentially like a resistor, and you wire it up like that essentially so that it can go in different places. I'll draw. It does ask you to draw the circuit, so I'll show you in 2 seconds. Yes, so the rheostat has a total resistance of 10 kilo-ohms, and then we have a selection of resistors available. So what we need to do is draw a suitable circuit that will provide this variable supply. And then we need to calculate the resistance of the additional resistor required, label components and the values, and then mark the polarities of the 9 volt supply and the output terminals. It's quite a lot in this question. I imagine it would have been quite a few marks. Essentially what you're going to have is, the first thing you know is that you've got a 9 volt supply. So I'll draw that here. I'll draw it as 2 cells. Don't think it really matters how many cells you draw, to be honest, but we'll draw it as 2 anyway. Okay, and we know there's a potential divider circuit, and we know that we're going to have a rheostat. Oh, this has gone a bit wayward. Doesn't really matter, that should be straight, but what can you do? Okay, so here is our rheostat. That shouldn't be a box, it should be resistor. And that is going to have our variable potential difference coming out. We need to be able to vary that between 0 and 6 volts. So our variable potential difference is going to be here, so that has to be between 0 and 6 volts. This is 9 volts. We know from the question that the total resistance of this is 10 kilo-ohms. 10 kilo-ohms, and then it's going to be attached to a resistor, which is what we're going to use to essentially make this whole circuit work. Okay, so whenever we use this, we know that there's 6 volts, a maximum of 6 volts across here, so there has to be a maximum of 3 volts across this one to make up our 9 volts. So if we remember from the last video that in series, the voltage is going to be given by this equation, where voltage of our potential difference across one component plus the next component plus the next component, la-di-da-di-da, is going to give us our total voltage throughout our series circuit. Okay, so this here is going to have a potential difference of 3 volts across it. So using that there, we will be able to tell where our what the resistance of what the resistor we need to put in is. Okay, so doing that, we'll be able to say that V equals IR, but we don't actually know the current at the moment. We're just going to be able to say that we need 3 volts. we need 3 volts. So what is our resistance going to be? Oh, sorry, this is silly. V equals IR. So voltage is proportional to resistance. We know that this resistor of 10 kilo ohms gives a maximum of 6 volts. So using our proportions, we can say that this 3 volts is going to have to be given by a 5 kilo ohm resistor. Okay, then what else does it ask us for? It asks for the output terminals. So on a battery, this is positive, this is negative. So therefore, this is going to be negative and this is going to be positive. And the reason for that there is you just follow the current round. There's negative, there's positive. Okay, so that is 3I. 3II, or 3 part 2, is a voltmeter of resistance 20 kilo ohms is connected across the output terminals. And the rheostat is set at its midpoint value. Then we have to calculate the voltmeter's reading. Okay, so now we've got in this part here, we're going to have our circuit, and I'm just going to draw it like this here for easiness because it's a little bit difficult to draw circuits on the iPad. And then we've got our terminals, which is going to have a voltmeter coming across it, coming across here. Sorry, I've drawn this a little bit wrong. This is going to be at the midpoint of the resistor. So if it's at the midpoint of the resistor, then the resistance of this is going to be equal to 5 kilo ohms. We know the resistance of this is going to be equal to 20 kilo ohms. So using our 1 over R parallel is equal to 1 over 5 plus 1 over 20. If we do that in the calculator, 1 over 5 plus 1 over 20 is equal to 1 over 4. So the resistance of our parallel circuit is going to be equal to 4 kilo ohms. And then we can use the equation V out is equal to R1 times the potential difference coming in over R1 plus R2. RP is our R1 in this case, so it's going to be equal to 4 kilo ohms, which is times 10 to the 3, times 9 over, it's going to be 4 kilo ohms plus 5 kilo ohms, which is 9 kilo ohms times 10 to the 3. So we're going to have 4 over 9 times 9, which is going to be equal to 4 volts. I think. Okay, so next question, question 4. I'm thinking this is now run on quite long. I might do this in a separate video. Have a go at it. If it's too difficult, let me know, and I will record a video and show you how to do it. All right, thank you very much, and I will chat to you soon. Cheers.